So as Musharraf said, I'm Rachit. I'm a postdoc here in AMP Lab, and today I'm going to talk about Succinct Spark. A very quick show of hands. How many people have attended a Succinct talk earlier or read about Succinct? Oh, wow. OK, great. So we have been working on this project for a while now. It's been almost 1 year, and very recently we released the first version of Succinct on Spark. And the goal is very clear that we wanted to do really, really fast interactive queries on Spark. And one of the fundamental challenges there was to keep as much data as possible in memory. And traditionally, the way to push more data in memory is compression. But when you think about interactive queries that you're talking about sub-millisecond or even, in a Spark, tens of 20s of millisecond queries, you really can't afford to decompress the data. And so we asked this very fundamental question that is it possible to do queries on compressed data directly without ever requiring decompression? And while we are still working on project very actively, it's one of the big projects in the lab. There are a lot of students in the project. We have made some progress, and that's what I want to share with you today. OK. So the first basic question is, what kind of queries are we going to talk about today? And this is slightly different from the general flavor of Spark that you may be used to. So I'm going to talk about something called point queries. And one way to imagine these point queries is search, or you want to do random access into some data. And why do we care about point queries? Well, there are some good companies that have done point queries fairly well. So Google and Bing. So search is one of the point queries. And then there are these new social media. With the rise of social media has given rise to these very new platforms. So Facebook supports search if you go to Facebook. LinkedIn, Twitter, all these companies that are supporting some form of search. Search is one of the very powerful primitives in big data analytics these days. On the other hand, then you go into Amazon, eBay, Walmart. Again, a lot of point queries. And then there are these new travel companies and hotels and restaurants. Everywhere you see a lot of point queries, interactive queries happening. So what is it that people use today? So today people use one of the two techniques. So suppose I have this, I'm going to use, just for illustration purposes, this file where I have different characters, just color encoded. And suppose I want to find all characters that are green colored. Okay? So one of the standard techniques, which also is used in a Spark, is data scans. And how do we do that? We store our input file, hopefully in memory, and then we start scanning. Okay? And really, is that slow? Okay? It's not just the animation. It is data scans are actually slow. Okay? Data scans are actually slow, but they're awesome in some sense because they have very low storage footprint. You just have to store the input file in memory, and then you can just scan the file, right? So you can push more data in memory. On the other hand, there are these super fast approaches, so-called indexes. So what you do is you take your input file, you pre-process the input file to create some sort of indexes. So over here is I'm just storing something called inverted index, which is for each of the distinct characters, I'm storing the offsets in the input file. Okay? So it's just a standard index. Now, what's the good thing about index? That whenever a query comes in, you just look up into the index and answer the query. So it's super fast. Okay? So unlike data scans, which are slow, indexes are super fast. But the problem is that they have high memory footprint because you have to store these indexes in addition to your input file. So the storage overhead is high. So if we want to look at this bottleneck from a slightly research perspective, we can start imagining this simple graph plot where on the x-axis I'm going to increase the input size. What happens if the input size increases? And on the y-axis I'm plotting the query latency that you would expect for a fixed infrastructure, so for a fixed cluster. So data scans look something like this. In particular, when the data fits in fast storage, the data scan latency increases with the input size. On the other hand, once the data stops fitting in memory, you see a slightly different slope of the curve, but they're still slow. If I look at indexes, on the other hand, they're super fast, when they fit in memory. So this is the place where indexes fit in memory, but since their storage overhead is high, they go out of memory very fast, and then their latency is kind of fixed once they go out of memory. And this is the cost you essentially pay by executing queries off slower storage. Okay. So now let me give you a very high-level overview of what Succinct does, and then I'll talk about Succinct as Spark. So what does Succinct do? Succinct takes your input file, and I apologize for this animation that's coming up in the next slide. Succinct takes this input file, and it pre-processes the input file. Okay, and it creates this suite of data structures. The nice thing is, and one thing which I want to really emphasize, is that Succinct is not storing the input file. All Succinct stores is just this compressed representation of the input file. Okay? And now, all the queries that I'm going to talk about in the next slide are executed directly on the compressed representation. Okay? So Succinct is not storing the input, it's storing just a compressed representation, and all the queries will be implemented, executed directly on the compressed representation. So the hope is that I'll be able to convince you that it gets low storage and low latency. So why is Succinct nice? Because we don't have to store additional indexes, which are considered a pain. We don't do data scans. We are essentially providing the functionality of indexes without actually storing any additional indexes. And we don't do data decompression, okay? Unless you want to read the entire data or you want to do data accesses. So let's look at this curve. Where does Succinct fit back? Since Succinct is storing a compressed representation, it can keep the data in memory for a much larger range of input sizes. At some point, Succinct will go out of memory, and then latency will be slightly worse than indexes. But this is the gain that you get by avoiding data scans in Succinct for these input ranges. And this is the gain that you get against indexes by avoiding going to slower storage. Okay? Okay. So we started designing the system from scratch, and we had to do a lot of interesting design decisions. The first design decision, and I'm going to talk a little more about it because we are very excited about it, is that Succinct exposes this very simple interface where all the queries are executed on flat, unstructured files. And I'll show you why this is such a powerful interface. So essentially, if I take this original input, Succinct is going to create these suite of data structures like I talked about. And then what kind of queries can you execute? The first query is search, okay, as I talked about, that you can find search. And here on the left, I'm showing the results on the original file. So first thing is that you can execute search, again, directly on this compressed representation. The second one is that you can extract or do random access into the data. So over here, I'm just extracting 5 bytes starting at 0 offset. You can do counts, so you can count for strings in the input file, and this is super fast operation. So in case you have some applications where you need really fast counts, it's really one of the things. You can append new data, and this is a Spark model that you can always append new data. And one of the interesting things is that you can do range queries. One very nice thing in Succinct is that range queries have complexity same as the original search queries. So range queries are also super duper fast in Succinct. Okay. So let me spend 1 minute on why we think that this flat file interface is so strong. So we started this flat file interface for Succinct, and then we implemented a lot of powerful abstractions on top of Succinct. So flat files allow you to analyze unstructured data, do queries on unstructured data. We implemented key value stores using this flat file interface, writing a simple serializer, which is less than, I think, 20, 25 lines of code. We can implement document stores like Elasticsearch, MongoDB, CouchDB, again, with 15, 20 lines of code, very simple serializer. We can actually execute queries along columns on tables as well, using, again, the same interface. And here's how it works. Suppose I have this very simple table. So I have 4 columns. What Succinct does is that it takes each column and it assigns it a unique delimiter. Okay? So these are the delimiters assigned to each column. And then it will append these delimiters along with the input data and write it out as a flat file. So for example, it takes this first column, takes the objects in the first column, appends the delimiter here, and writes down the objects. Okay? And now see why it is interesting, because when a query comes in that is asking for, say, green objects in column 1, all I have to execute is that green object appended with the delimiter, and you will get the right results. But the beauty is that using this simple interface, now you can implement all these very powerful abstractions right on top of Succinct, writing a very simple serializer function. Okay? Okay, so let me now talk about Succinct to Spark a little bit. Why is Succinct to Spark interesting? We think it may be interesting for multiple reasons for different people. So one thing is that you should already be using a Spark, which I hope all of you are. What Succinct to Spark allows you to do is get some new functionalities on top of Spark. It allows you to use a Spark as a document store. You can even use it as a key value store. But the interesting thing is that now you can do search on documents. So for example, Elsevier people were interested in storing all these massive documents on Succinct to Spark, on a Spark, but now being able to search on the documents without actually scanning all the set of documents. The second thing is that you can actually use Succinct for faster operations on RDDs. You can now get random access into RDDs. Anybody who has tried to do random access on RDDs knows that RDD has to do full scan of the RDD to actually get random access. Now you can do Succinct. You can use Succinct to get random access on RDDs. And you can implement some of the filters really, really fast. And the most interesting thing is that you can push more data in memory. You can execute more queries in memory, so you get benefits. Okay, so now let me talk about Succinct RDDs for unstructured data and give you a very quick overview of what the API looks like. So it starts very simple as standard. You import some classes. You create an RDD. Over here, I'm just creating an RDD, which is an array of bytes. And then you succinctize it. You compress it using Succinct, using a very simple command, .succinct. Now, once you have compressed the original RDD, then you can execute all these powerful primitives on top of that. For example, over here, I'm showing you .search. So you can just use .search, and you don't have to worry about anything else. Succinct will do everything for you. So you can search for example, Berkeley in these documents. Okay. Another thing is .extract. So again, Succinct RDD is giving you the abstraction of the interface of just doing extracts, and you can do arbitrary extracts and arbitrary offsets and arbitrary lengths. And the third thing is .count, so you can count. The nice thing is, take this slide and then just replace Succinct RDD by Succinct KVRDD, and you get the same things on KeyValueStore. So again, the same thing. I've constructed here a KeyValueStore, an RDD with keys and values, and I succinctize it. And then you can do just .search, now on Succinct KVRDD, and now you get all the keys whose values contain the search term, okay, rather than offsets. So now you can deal with keys and values, okay. The same thing here, you can get you can get a value for a corresponding key. Nice thing is that for some cases, you may also want to get random access into the value itself, not just using get interface. So we allow you to do .extract as well into the values. Okay, so imagine a Wikipedia document where you can search for all the document IDs where Wikipedia contains Berkeley. Then you can do an extract. You can get the entire document by doing a get, and then you can even go into the document and extract certain bytes by doing an extract. So let me show you some numbers very quickly. So we used with this Wikipedia data set with 40 gigabyte of data. We used Amazon EC2. Notice that we are using 120 gig RAM so that all the systems fit in memory. So this is not Succinct at its best. And then we created some search queries with different number of occurrences, and I'm going to show you some numbers against Spark and Elasticsearch. One nice thing to notice here, one important thing to notice here is that when you're using Elasticsearch, you might have two different goals. One is getting low latency, and the other one is getting high throughput. Spark is probably not the right platform if you care about user-facing high throughput queries. So I'm going to talk about only low latency part, not the high throughput part. And the caveat is that some of the numbers are data set dependent, so be careful there. So let's see what the search results look like. So here's some very simple graph where I have a Spark where things are on disk. We haven't cached them. So one thing is that notice that the y-axis is on log scale. So just scale it up when you see the difference. Then we run a Spark in memory, and you get some performance benefits, roughly 3x better. And then you run Elasticsearch. This Elasticsearch is outside of Spark, so it doesn't have those overheads of Spark job execution time and everything. And it actually gets, roughly 30x better than a Spark, which is brilliant. And then we implement Succinct on top of Spark, and as soon as you run Succinct on top of Spark, you get 2.75x better than Elasticsearch. So this is excellent. Okay. So you get really fast Elasticsearch. The nice thing is that all the systems fit in memory, at least the last 3 graphs. And we are still giving you more memory efficiency, so you have 2.5x lower memory footprint compared to Elasticsearch or Spark. Okay. So let me talk about, so this was the Succinct to Spark release. Let me talk about what is next. So we are doing a lot of interesting work. The first thing I want to announce today is that we have this very exciting project of supporting regular expressions on Spark, again, using Succinct. So imagine doing regular expressions directly on compressed data. I think it would be a very powerful functionality if we can do that. The second thing is that we are working about new data types, so supporting JSON documents, for example. And we are looking for new abstractions like batch updates within Succinct. So as I said, these were next steps for Succinct, but these were next steps only until yesterday night. I'm very happy to announce that we actually support this already. So there's one very exciting thing about Succinct, that you can now execute regular expression matches directly on compressed data. We are very excited to say that you can now do it directly on Succinct. So support for regular expressions, I think, is a very exciting project. We are very excited about it, and I want to say a little more about it. There are a lot of applications for regular expressions that we don't think about in regular expressions, like data cleaning, information extraction, bioinformatics, and I think this is going to open up a lot of opportunities for Succinct to Spark and Spark in general too. And we support most of the operators that you think about, and one very simple example is, I don't know why anybody would like to search for Stanford, but if you wanted to search for Berkeley or stanford.edu, this is one of the things. So let me show you some RegEx numbers. So again, the same kind of plot. We have a Spark on disk. Okay, so you get, again, the y-axis again on log scale. The Spark in memory, not too much benefits actually, because it's pure scans, so we don't get much benefit when we keep a Spark in memory. Elasticsearch is still faster, almost 20x faster still. So getting close. Again, once you run with Succinct, you really get roughly, over here you see much more benefits, almost 7x better. Okay, so you can do regular expressions on Succinct to Spark while getting memory benefits. And one thing I want to note is that we also have a standalone implementation in C++ of Succinct, and that is still, roughly speaking, 80x faster than Spark. So if you wanted to run that, and I think this shows that there is a lot of improvement to be done on the Spark side as well in the scheduling layer. So on Succinct RDDs, now you can extend the API to do regex search, and you can actually run regex queries. And on Succinct KV RDD, you can do the same thing just by replacing search by regex search, and enjoy it while it lasts. So support for JSON. Again, just replace Succinct RDD or Succinct KV RDD by Succinct JSON RDD, and you can do search for JSON documents. You can filter documents, which means that you can specify specific fields in Succinct JSON and get the results. And you can obviously do random access for JSON documents. OK, how much time do I have? OK. So what is really, really next? OK, so we have a lot of exciting projects going on in the lab on Succinct. There are 7 or 8 students working on different areas in Succinct. And 2 things that I want to mention is in terms of improvement. So one thing I didn't say is pre-processing. So of course, when you Succinctize your RDD, it takes a little bit of time. Okay, so you don't want to use Succinct if you want to run only 1 query, okay, or 10 queries. If you have a cluster that's running for a day or a few hours, I would highly recommend using Succinct. But we are doing a lot of work in making pre-processing really, really fast, and better support for scans, because sequential throughput is kind of low in Succinct. So if you have queries where you have to scan the entire data set, then you have to decompress it, and this is a standard problem. But we are trying to make it faster. We are doing a lot more integration with the Spark ecosystem, including data frames and building a lot of applications that I talked about, especially in terms of RegEx. There are a lot of interesting applications. We're doing a lot of testing and benchmarking, especially with regular expressions. It's really hard to do benchmark in the academic setting, so we could use your help. Give us some standard queries. Tell us what kind of workloads, what kind of RegEx queries, and we can do a lot more optimization on that front if you're interested. And finally, we are working on some very interesting new functionalities. And I want to say two things. The first functionality is that we are working on some extensions on Succinct where we are trying to give you the functionality of doing queries on both compressed and encrypted data. So if you have any applications where you want to get confidentiality while getting compression, that's one of the things. And we are also giving you we are also working almost done with a functionality where you can actually choose along a smooth memory latency trade-off of how much memory you want to set, how much compression you want to get. And this is one of the very, very super exciting projects in Succinct. And a few surprises that I'll keep it for the next talk. So that's it. If you have any questions, please feel free to write to me, Anurag. In the remaining, I was really fast today. So I'm known not to be fast and extending my talks far beyond my talk time. But today, I finished a little early because we want to show you how Succinct actually runs in practice. We are going to give you a demo. Okay. And of course, Anurag is one of the guys who has been doing all the work. I just give talks. So, if you are happy about the project, he's the guy to say. So he'll be showing you how Succinct actually works in practice. So we're going to switch.
This is a demo where we've used a Wikipedia dataset of about 10 gigabytes, 9 gigabytes of raw data. And as you can see, this is the dataset on HDFS. It takes about 9 gigabytes, 1.8 gigabytes per partition into 5 partitions. And
it might not be visible in the end, so.
Yeah, I might want to.
So over here, we have one single server with 5 partitions running on top of a single server Spark. And over here, you see these 5 partitions. They are just showing 1.8 gigabyte each per partition. This is raw data, so 9 gigabytes of data.
Yeah. Over here, we have the same data when encoded with Succinct. So as you can see over here, each of the partitions is now 1.2 gigabytes. So that's roughly 6 gigabytes after compression. And this is the exact same setup we have for both of these systems. One is just uncompressed, and the other is compressed using Spark. And the third system we have is Elasticsearch with the data loaded, exact same data. And once you load the data into Elasticsearch, you'll see that the storage footprint is close to 13.5 or 14 gigabytes, as you can see the number reported by them over here. So what I'm going to do is run about 1,000 search queries, as Rachit talked about, on all 3 of the systems and see how much time each of these systems take to execute all 1,000 search queries in real time. So I have a script that will just start.
One thing to note here is that Elasticsearch is running out of Spark. So,
it's a standalone system. Yeah. So I have this script that essentially makes all the systems go. And OK, it looks good. And we're going. So this is live, all of the queries running on the 3 systems simultaneously. And this is essentially a progress of how the queries are being executed on all 3 systems. And as you can see, Succinct is slightly faster than Elasticsearch. I'm sorry if you can't see the side. And
you're not allowed to make jokes on a Spark on this.
Yeah, it's catching up. So it did one. Okay.
All right, I guess that's a good point to stop. So we are don't use data scans for search. But thanks a lot. We are very excited about this project, and we would love to get feedback from you. Please talk to us, tell us about your use cases, and I'm sure there will be a lot of interesting things happening around over the next few months. So I can take a few questions if you have any. Okay. Aha. Yes, so the question is whether we are going to support Parquet. 2 days? No. Yes, we have a lot of integration going around with data frames. We already have a working version that you can actually use now. What we wouldn't recommend you to run is full-fledged SQL queries, because there are a lot of operators that we need to optimize that are not very. So imagine a lot of SQL operators have to do data scans, and that is one thing that we are very actively working on. But if you want to execute some simple filters or something, absolutely, you can use Succinct on top of Parquet now. Yeah. Look at the data frames API on Succinct web page. Yes?
So for this model set, what was the Succinct pre-processing time versus the Elasticsearch indexing time on the same hardware?
So on a Spark, Succinct pre-process the data roughly 4 gigabytes per hour per core. Okay, so per hour per core is 4 gigabytes. Okay, I think there are two things. If you knew that you had a long-running cluster, right, you could pre-process using Spark without doing the way we are doing right now, which is if you give the data, it will pre-process and load the data on the same machine. I think you can parallelize it really fast and then bring it back and push the data on a fewer machines. There are two problems with pre-processing. One is that, as you would imagine, when we are pre-processing the data size blows up slightly. So we are kind of limited with how much data you can pre-process on a single server. Right now, we are doing 4 gigabytes per hour, but we are hoping, this is one problem that we haven't solved really. We haven't sat down and solved the problem, but now we are on to solving this problem. So I promise you, we'll be solving this problem very well. Yeah. But does that answer your question? It's 4 gigabytes per hour per core, so it's not very fast. So yes, so we will. What I want to say is that I would expect the use cases would be where you have to append more data. Yes, that is what we are already supporting, like announced today, that you can append new data onto this. But if you wanted to do in-place updates, I think it would be not sufficient to use Succinct for in-place updates, the data where you have to do in-place updates. Does that answer your question? Yeah.
So Elasticsearch allows you to have very sophisticated indexing so that you can search for misspelled words, things like that. What kind of support does Succinct have for more complicated ways of indexing?
I don't know of many searches which are more complicated than regular expressions, but maybe I'm wrong. For example, yeah, we don't support fuzzy matches, for example, which Elasticsearch does, right? Yeah, that is one thing. Approximate matches that we haven't worked on yet. If there are interesting applications, like I said, talk to us. This is a very recent project, and we'll be happy to. But I think regular expressions is, to me, a very powerful thing already. Elasticsearch supports that, but in a very crude way. You know, but yes, if you have more functionalities that you would like to see, please talk to me or Anurag or Jan or anybody in the lab.
Let's thank the speaker.
Okay, thank you.